Continuing our global warming discussion. On this graph, the different color lines are the results from different models. From the year 2000 to the year 2100, what is temperature expected to do? Right, rise. By how much? From about 2 to 5 degrees Celsius, which is about 3.6 to 10.8 degrees Fahrenheit. That's quite a bit. Hopefully, the predictions are higher than what will really happen, but these are our best, very educated guesses. We'll have to see what will really happen, and we are not entirely powerless to do something that might significantly impact these scenarios, but only time will tell. So why is the planet warming anyway? You might already know. You might have heard of the greenhouse effect. Earth's temperature depends on amount of sunlight received, amount of sunlight reflected, and amount of re-radiated heat that is retained. Earth's energy balance is out of whack a bit, with currently more energy coming from the sun than is lost to space. We are gaining about 1 to 2 watts per square meter more each year. 1 watt is about 1 LED Christmas bulb light. So just imagine the Earth decked out in lights, with 1 to 2 lights per square meter. Kind of pretty. So why are we keeping those extra watts? Well, sunlight received is short wave and visible. The sun's short wave radiation is absorbed mostly by the Earth and a bit by the atmosphere. The Earth, which is not as hot as the sun, obviously, re-radiates mostly long-wave infrared radiation. And most of the long-wave radiation is released into space, but some is absorbed again, which warms our planet. Here is an image showing short-wave electromagnetic radiation from the sun and long-wave electromagnetic radiation from the Earth. Here's what the words say. Energy input. Close to a third of the energy that descends on the Earth from the sun is reflected or scattered back into space. The bulk of the remaining incoming visible solar radiation is absorbed by the Earth's surface. Energy output. The atmosphere transmits outgoing infrared radiation from the surface. Most of the outgoing radiation, after many scatterings, absorptions, and re-emissions, is emitted from levels near the top of the atmosphere. Most of the radiation originates at the Earth's surface, and the bulk of it is absorbed by greenhouse gases at heights on the order of 100 meters. By various atmospheric energy exchange mechanisms, this radiation diffuses to the top of the troposphere, where it is finally emitted to outer space. There is a very small imbalance of the Earth's energy balance today, i.e. more solar energy arrives at Earth than leaves, of about 1 watt per meter squared, and this warms the atmosphere and oceans and melts glaciers. Here you can see what we mean by electromagnetic radiation. It's a scary word for some people, but when you call it visible light and AM radio, it's suddenly not so scary. You may recall from some previous science class that hot bodies emit short-wave electromagnetic radiation, and cool bodies emit long-wave electromagnetic radiation. What type of bod do you have? Are you hot or cool? Do you emit visible light, or do you just warm your surroundings? Okay, silly joke, but hopefully helpful in remembering stuff about electromagnetic radiation. The sun is a very hot body, especially compared to the Earth. Thank goodness. Interestingly, the peak radiation is in the visible light spectrum, which I like because I like to see. In contrast, radiation from the Earth has much longer wavelengths in the infrared or heat spectrum. These much longer radiation waves are because it is a cool body compared to the sun. Greenhouse gases, such as water vapor, carbon dioxide, methane, and chlorofluorocarbons, absorb long-wave radiation and are warmed. This makes the lower atmosphere much warmer than if the radiation escaped into space. On the graph below, we have electromagnetic radiation wavelength in microns on the x-axis. On the y-axis, the top bar is radiation intensity. And the other bars are 0 to 100% absorption. These bars are each labeled with different gases in our atmosphere. What do you notice? Can you see how much of the shortwave solar radiation passes right through our atmosphere? Can you see how the long-wave Earth radiation is absorbed by different gases? Look a bit to the right and left of the peak Earth radiation. Now, all greenhouse effect is not bad. The greenhouse effect is a natural and necessary process. Without any greenhouse effect, the Earth would be 33 degrees Celsius cooler. Brr, meaning that all surface water would be frozen, and little life, as in not much life, would exist. Most of the natural effect is from water vapor and water droplets. As you can see in the pie chart, water totally wins. A far distant second is carbon dioxide. But no one is saying reduce water vapor emissions. Part of that is the residence time of these gases in the atmosphere. Water cycles through the atmosphere approximately every 9 days, meaning precipitation and evaporation happen pretty quickly, all the time. In contrast, carbon dioxide has a much longer residence time in our atmosphere and near surface oceans, on the order of decades to centuries. Also, we as humans are adding a whole lot more carbon dioxide to the air than nature would normally. Not so with water. So that's why your carbon emissions are troubling, but your water vapor emissions are never mentioned. Maybe your water use, but not your water vapor emissions. Human activities have increased amounts of some greenhouse gases. This is the anthropogenic, human-caused component of warming and includes gases such as carbon dioxide, methane, nitrous oxides, and chlorofluorocarbons. So just looking at the anthropogenic greenhouse gases, carbon dioxide accounts for most of the anthropogenic greenhouse effect, though only 0.0387% by volume of the atmosphere. In the past 160,000 years, concentrations have varied between 200 parts per million and 300 parts per million. At the beginning of Industrial Revolution, about 1860, CO2 was about 280 parts per million. The concentration of carbon dioxide as of November 2015 is 400.38 parts per million. And it is predicted to reach at least 450 parts per million by the year 2050. And the present level is higher than at any time during the last 800,000 years, and likely higher than in the past 20 million years. For reference, humans start about 2.5 million years. So this carbon dioxide level is higher than anything we have experienced as a species. The table to the right shows a rate of increase and relative contribution of several greenhouse gases to the anthropogenic greenhouse effect, the part that's our fault. You can see a couple things. First, you can see water vapor is not on the table. because it is not considered an anthropogenic-caused greenhouse gas. Second, of the gases in the air that are considered our fault, carbon dioxide wins. Interestingly, molecule by molecule, methane, CH4, is a way more potent greenhouse gas than carbon dioxide. But there is just so much more carbon dioxide than methane, and also the residence time of methane in our atmosphere is on the order of only about 10 years as compared to carbon dioxide, which may stick around in the air and near surface oceans for centuries. But even if we are not influencing climate, average global temperature fluctuates. The next few slides look at global temperature change of long to short timescales. Change in temperature will be on the y-axis and time will be on the x-axis, but you will need to pay attention to the scales for each, which vary quite a bit. Over the past 800,000 years, low temperature coincide with major continental glaciations, and high temperatures with interglacial periods. Over the last 150,000 years, we see the previous major interglacial period called the Eocene, when sea level was 4 to 6 feet higher than today. The rise in sea level didn't affect us here in Idaho, but it definitely affected coastlines. Over the past 18,000 years, we can identify a cold interval called the Younger Dryas, which occurred 11,500 years ago, followed by warming to the Holocene maximum, and then more recent cooling, called the Little Ice Age. Over the last 1,000 years, we see several warming and cooling trends in the framework of the medieval warm period and the Little Ice Age. Interesting to note that it was during the medieval warm period that the Vikings sailed to Newfoundland and started growing grapes. Their settlement failed tragically. But grapes in Newfoundland? What were they thinking? Well, it was warm for a while. Climate change can be a doozy. Over the last 140 years, we see a continuing warming trend that began in the 1750s until 1940s. From 1910 to the present, global temperature generally rise about 1.4 degrees Fahrenheit in the past 100 years. And we know that temperatures in the past 30 years are the warmest since monitoring began. So that's the end of our brief tour of recent climate fluctuations. So why does climate change? Any ideas? Well, let me tell you about Milankovitch. He dedicated his life to explaining climate mathematically, and he determined that there are changes in our Earth's orbit and tilt that affects the amount of insolation received electromagnetic radiation from the sun, and therefore affects our climate. The natural changes in Earth's movement around the sun are called eccentricity, tilt or obliquity, and precession. The eccentricity is the orbit shape, and this change occurs from more circular to more elliptical about every 100,000 years. The tilt or obliquity changes from more tilted rotation to more straight up and down rotation compared to Earth's axis. This change occurs about every 40,000 years. The precession or tilt wobble is a change in the leaning of the Earth or direction of tilt. This change occurs about every 20,000 years. See the supplemental video for more information.